Okay, welcome to the screencast for naming and writing formulas for ionic compounds. So here's your essential question, and we're going to go through the nomenclature, which is naming, and how to write formulas for various types of ionic compounds. There's a couple different types that we're going to go through, and then I'll show you polyatomics. So, naming compounds and writing formulas. So this is the unit of nomenclature. Nomenclature is just the assignment of a correct and unambiguous name to each and every chemical compound. Unambiguous means that each compound is going to have a different name. Common names can cause confusion, especially if you're talking about multiple languages or people aren't as familiar with some substances as others are. So common names are not something that we want to rely on and use, so we have to have some sort of kind of a systematic naming system. And then we're also going to write formulas. So what is a formula? It's a representation of the fundamental compound using chemical symbols as well as numerical subscripts. So in the formula, it's like the shorthand. You're going to use the symbols for the elements, and then the subscripts tell you how many atoms of those elements you have. So writing names and writing formulas. All right, so ionic compounds, as I hope you remember, are always between a metal and a nonmetal. And so you have your metal first, your nonmetal second. Those usually react to form ionic compounds. The metals are cations and the nonmetals are anions. So in a formula, you're going to write the formula using the smallest whole number ratio. We don't use fractions. You don't see like half of an atom of this or a quarter of an atom of this. It's always going to be in whole number ratios, and it's going to be the most reduced for an ionic compound. And there are two types. This is where we get to deal with those lovely transition metals that don't follow the rules. So the first type is what we're going to call a type 1 or a type A metal. On the periodic table, these metals are in column 1, column 2, or column 3. We know the charge of them. So they're either a 1+, a 2+, or a 3+. The alkali metals, alkaline earth metals, and then the boron group. We know these guys have a 1+, 2+, or a 3+ charge based on their valence electrons. So a type 1 ionic compound is a metal in column 1, 2, or 3 bonded to a nonmetal. A type 2 ionic compound is where you have a transition metal, a metal that's not in column 1, 2, or 3, and you don't know the charge of them. So those ones in the middle, as well as the ones underneath the staircase, and the inner transition metals on the bottom. They don't really follow the rules, so we don't know their charge. So that's going to be a type 2 ionic compound. And we have different rules for both of them. So we're going to go through the type 1 first, because they're kind of the easiest, most basic ones. So how do you write the formula? Well, you just balance charges. This is what we started doing with the ionic compounds when you were drawing them out. You notice that you had like 3 lithiums bonded to 1 nitrogen, so it's Li3N. You're just balancing the charges. Your positives and your negatives have to balance out. They have to give you a net charge of 0. Compounds are neutral. So you use the oxidation number, you use the charge to determine, which is based on the number of valence electrons, to determine how many valence electrons it needs to gain or lose. So the cool thing is with a type 1 ionic compound, you know the charge of the metal. It's either 1+, 2+, or 3+, and you know the charge of the nonmetal. It's either a 3-, a 2-, or a 1-, and then you just match them up, make them balance out. When you're naming them, and I'll go through a few examples here in just a little bit. When you're naming them, there's a couple of rules, just very basic. When you're naming the cation or the metal, you just keep the name the same. And when you're naming the anion, you change the ending to IDE. So this is why, like sodium, when sodium and chlorine are bonded together, it's called sodium chloride. You keep the name of the cation the same, and you change the anion to IDE. So looking at some of these examples, like here is the cation name for sodium, and then the anion name would be chlorine, but you change it to chloride. And when you put them together, you get sodium chloride. Here's sodium oxide, lithium sulfide, aluminum bromide, calcium oxide. When you're writing the formulas, you balance the charges. So sodium's a 1+, chlorine's a 1-, so I just need 1 of each of those to cancel it out. Sodium is a 1+, oxygen is a 2-, so I need 2 sodiums to cancel out the oxygen. Lithium's a 1+, sulfur is a 2-, so I need 2 lithiums. Aluminum is a 3+, bromine's a 1-, so I need 3 bromines to give me a net charge, to have the same number of positives and negatives. So try to go through and write formulas for sodium and oxygen, lithium and bromine, aluminum and oxygen, as well as writing the names, and we're going to go through these examples in class together. So I just want you to try it and see if you can do it. These are ones you know the charges for, so it makes it at least easier. So follow the formula rules and the naming rules and see if you can figure them out. Okay, a type 2 ionic, this is where they don't quite follow the rules. The metal is not found in column 1, 2, or 3, so you don't know what the charge is. You look at the periodic table and go, I don't know, like manganese is right in the middle. Iron is right in the middle. Cobalt and copper and nickel and mercury and lead, all those. I don't know what the charges are for them. They're not in column 1, 2, or 3. So it makes it kind of difficult to write a formula for it. These are your transition and intertransition metals. And ironically, or what's cool about them is they form multiple ions. They don't just form one ion. Like everything in column 1 only forms a 1+. Everything in column 2 only forms a 2+. These guys might form a 5+, a 4+, a 6+. We do know they're all positive because they're metals, but we don't know exactly what charge they form. So we have to use a different system with them. We have to use the stock system, and that's why I've put it in bold so that you can see the stock system. There's going in the name of these compounds, so in the name, not in the formula, but in the name, there's going to be a Roman numeral after the name of the metal, and that's going to tell you the charge of the cation. That Roman numeral has to be there. If it's not there, then you don't know what the charge is to be able to write the formula. So like, for example, FeCl3, when I look at this compound, chlorine is a 1- charge, and I have 3 of them. So that tells me that my iron has to be a 3+, and instead of naming it iron chloride, I actually have to name this iron 3 chloride. The 3 tells me that that iron is a 3+. So I have to include this Roman numeral. Usually you'll only use the Roman numerals of 1 through 10, but I have to use the Roman numeral in the name instead of just writing iron chloride to determine the charge, or to tell me the charge. This next one down here is FeCl2. Well, chlorine is still 1-, and I have 2 of them, so I have a total of 2-, which means that that iron has to be a 2+. So in this case, it's not iron 3, it's iron 2 chloride. And I show the distinction between them by putting the 2 in Roman numerals. So what's in the Roman numerals is the charge. So how do you write the formula for these? You still balance charges. You know the charge of the nonmetal. You know the charge of what it's bonded to, so you figure out what the total negative charge is, and then that tells you what the charge of the metal has to be, because remember, they have to balance out. So if I have a nonmetal that's a 3-, then my metal has to be a 3+. And when you're writing the name, you name the metal like normal. You change the anion ending to IDE, except with these, you're going to have to report the charge as a Roman numeral in parentheses right after the name of the metal. So instead of just writing like sodium chloride, you would have to write nickel 3 oxide. You would actually have to put something in Roman numerals. So here are some practice problems, and we will go through these in class, but I want to see if you can figure them out or go through some of the practice for these. So manganese 2 bromide, tungsten 5 oxide, iron 3 sulfide. And if you don't know what the Roman numerals mean, on that cheat sheet that I gave you for the polyatomic ions at the bottom of the page, there is a box that has all the Roman numerals in it, 1 through 10. And then writing the names. So we have V2O3, HGSE, and CU3P2. So see if you can write the names for these. These are all type 2. So see if you can follow those rules and figure them out. And if not, no big deal. We're going to go through this in class. So what we've been working with so far are what we call monoatomic ions. Mono means 1. So these are ions that are consisting of a single charged atom. So these are the ones you find on the periodic table. You're only going to have a metal bonded to a nonmetal. It doesn't always work that way, though, as you see on that sheet of polyatomic ions that I gave you. Sometimes ions can be composed of 2 or more atoms bonded together with an overall positive or negative charge. So they're not a compound because they still have a charge. They're not balanced or happy, but they are an ion that can now work as one unit and bond to something else. So I've provided you with a list, but here's some examples. Ammonium ion is NH4+. sulfate ion is SO4 with a 2- charge. Here's a whole list of them, and like I said, I gave you that cheat sheet, so go ahead and get that out because you're going to need that. I'm not going to make you memorize these because they're too easy to look up, but just some common ones. Hydroxide is OH with a 1- charge. Cyanide is CN with a 1- charge. Phosphate is PO4 with a 3- charge. And if you look at these, it gives you the formula and the name for all of them. So this makes it really nice and easy for you. So when we talk about polyatomic ion compounds, there's really 3 types that we're going to see. A metal bonded to a polyatomic ion. Remember that metal can either be a type 1 or a type 2 metal, so you still have to use the stock system here. Or a polyatomic ion bonded to a nonmetal, or a polyatomic ion bonded to another polyatomic ion. The cool thing is you're still dealing with a positive ion bonded to a negative ion. It's just depending upon whether you're going to use the periodic table or the polyatomic ion chart. But you're still going to be balancing charges. So when you write the formula for these, you're still balancing charges. The positives must equal your negatives. But because the polyatomic ions are groups of things, if I need multiples of that group, I'm going to have to put it in parentheses. And I'm going to just use the charges provided on the chart. I don't have to calculate the charges myself. If it says it's a 3- charge, then that's the charge that I use for that polyatomic ion. And when you're naming them, it's just as simple as writing down the name of the polyatomic ion. So if something is bonded to ammonium, I would just write ammonium. I don't have to worry about changing the name. Use the stock system if needed. Remember, if it's something that's bonded to a type 2 metal. And change the ending of the nonmetals to IDE. So if I have a polyatomic ion bonded to a nonmetal, I still have to change the ending to IDE. Like ammonium bonded to chlorine, I would call it ammonium chloride. So you still have to follow those previous rules. So that's the example that I just gave you, was ammonium, NH4 is a polyatomic ion bonded to chlorine, and because that's a nonmetal, I would change the name to chloride. So go ahead and see if you can name these compounds. I want you to see here, we have, an element bonded to a polyatomic ion. So we have a metal polyatomic ion. Here's a metal polyatomic ion. Notice that there's parentheses around this polyatomic ion. And there's parentheses because I need 3 of that whole group. So I have to put parentheses around it because I don't just want to write FeNO3 that'll look like FeNO33. And that is definitely not the correct formula. This one I didn't have to put parentheses around it because HCO3 is the polyatomic ion. So if you look on the chart, you can find HCO3. And I only need 1 of those. That's why there's just 1 listed. So go ahead and see if you can name these compounds. Remember to follow the rules for metals. If it's a type 2 metal, you have to use the stock system. And then see if you can write the formula for these. So this is a metal bonded to a polyatomic ion. This is a polyatomic ion bonded to a nonmetal. Here is a metal polyatomic ion, metal polyatomic ion. See if you can go through and figure out these examples, and we will go over them in class.